energy initial equals energy final. Initial kinetic plus initial potential is equal to final kinetic plus final potential. That should hopefully not look unfamiliar to you. 1/2 mv initial squared plus.
Is that a U?
That's supposed to be a U. Now we're dealing with gravitational potential, but we're not dealing with mgh, because as this thing launches, little g is not constant by any stretch of the imagination. So we have to use the generalized formula, which I'm not deriving for you because it involves calculus, but I will just present to you negative big G, mass of the object, mass of the planet, over the distance between them squared. Distance, no, not squared, distance between them, is equal to 1/2 m initial, that's over object. Mass of object, Vf squared minus big G, mass of object, mass of x, over R final.
Why is it subtracted?
Because the formula is negative big G. It turns out that the negative means that there's an attractive conservative force going on.
Say that one for the attractive conservative force, what does that mean? That means it's trying
Gravitational force is always an attractive force.
to, it's trying to pull it down.
Yeah.
Okay.
All right.
Wait, hold on. So, we've said pulling it down means negative. Like, why can't I say, okay, I want this to be, like, I want gravity, I want downward to be positive. So like for this equation, I say downward is positive. So
When you are setting up the equations, when you're deriving the equations, as you get closer, as the masses get closer together, you are going to a smaller potential energy. That's in essence.
Okay. So
It's
losing
built
magnitude.
into it.
You're losing.
No, it's becoming a smaller number. So if my potential energy initially, say my potential energy here is negative 10 joules, as it falls, it'll become negative 20 joules or whatever it is. It becomes smaller. Not the magnitude necessarily smaller, just the number itself becomes smaller.
Okay.
What,
All right.
What does R stand for?
The distance between the centers of masses.
So like middle of the planet, middle of the object?
Yes.
Okay.
We assume that the object is small in comparison to the planet. All right, so what's zero?
Initial speed?
Oh,
No.
better not be, because initial speed, that thing's not going anywhere. It's already, we're starting the problem with it's already launched.
Finals, not for this continuing to go, right?
However,
Wait, final speed. Should please you.
close enough. This is the mathematician versus the physicist. Mathematician, it will never be zero. The physicist, close enough. It gets slower and slower. We're trying to find that we're trying to find a minimum speed so that it won't come back. If I take it way beyond that, yeah, it will never be even close to zero, but we're trying to find that minimum speed so that it won't come back, so that final speed is incredibly tiny. Farther out it gets, there's less gravitational pull, so the acceleration is dropping off as well, magnitude-wise. All right, so this is zero because VF is approximately 0 meters per second. All right, we can let one other thing be zero.
Final gravitation.
Why?
Because you escaped it. Almost.
Mathematically, what's changing as it gets farther out? How is the object changing? Is this an existential Buddhist thing? Some Zen?
The distance between the two centers would change.
Yeah. So R here is getting bigger and bigger and bigger. If I take a fraction and let the denominator get incredibly big, what happens to the value of the fraction?
It gets smaller and smaller and smaller and smaller. So it's pretty much zero.
So RF goes to infinity. Therefore, fraction goes to 0.
But how can it go to infinity if the final speed is 0? Like, how can it keep going for?
I never said the final speed was 0, I said it's close to 0.
Okay.
It's incredibly tiny, and then you square it, it's gonna be even tinier. It's gonna have no significant impact.
Okay.
Just as this won't ever actually be 0, but it'll be incredibly tiny. All right, so what we're left with is, well, there's no energy. Now remember that all the potential energy formulas have plus some constant, so if you want to give it some energy, you can always do that, but it'll cancel out. This is what we're trying to find. So I got 1/2 times the mass of the object times some initial speed squared minus big G, mass of the object, mass of the planet, over what is the initial distance? Wow, if that's 0, then we got an infinity, right? Negative infinity.
Well, we would need to know, or would we need to know the middle of the planet? Can we figure that out? Without
No, we will assume that we know, well, what dimension are you looking for there?
the distance between the two, like R?
Okay, in essence, it's that distance right there.
Yeah.
So we'll just label it as radius of the planet.
Would we be given that on a problem, or are there ways to figure that out later down?
You would have to be given it or given enough information to figure it out, but as far as this course goes, you'd probably be given it. So here's our formula right here. I can cancel one thing out at this point, because I do have a common factor to every term.
I don't know.
The mass of the object is irrelevant once it's launched. Now, it makes a difference to launch it, but it doesn't make a difference once it is launched. So I'm left with 1/2 V initial squared is equal to big G, mass of the planet, over the radius of the planet. So my initial speed, 2G mx over Rx square root. That is the formula for escape speed.
There you go, it's almost there with the escape idea.
And if you plug in the values for the Earth 1, the square root of 2 times 6.67 times 10 to the negative 11th times mass of the Earth, 5.98 times 10 to the 24th, divided by the radius of the Earth, 6.38 times 10 to the 6th. You get a number that's a little bit more than 11,000, 11,100. It's a little more than 11,000 meters a second.
The equation was called the escape speed.
Escape speed, yes.
Is that 28 or 20, 10 to the 28? They're 5.8, 5.98.
24. And sort of just a teaser, if there's a maximum escape speed, or a maximum speed, of which in semi-classical physics, it comes out that the speed of light is a maximum speed. If the speed of light is a maximum speed, then if you solve for R, you basically can figure out the size given how small a mass needs to be in order to create a black hole. But that will be saved for another day.
So we'll
You're
create
saying
black holes another day.
That's right.